All right, back to recording. So this section is a little mathy. This section is a little mathy, not complicated mathy, but it is a little mathy. So this is chapter 24, and it is on, and remind me, how am I doing this for this class? Because we don't have an ebook. Oh, I'm writing things that I'm holding up on paper, right? That's what I've been doing. Okay. So chapter 24. And this is on the chi-squared test. The chi-square. Chapter 24, the chi-square test. Let me spotlight me. I'm not sure if you guys see me big or not. Okay, the chi-squared test. And as complicated as it sounds, it's actually not that bad, the chi-squared test. And the chi-squared test is a test that we use for testing for basically two things for this course: independence of two categorical variables, and for what's called goodness of fit tests. A goodness of fit test is you're checking how good a certain fit is. Like, oh, I believe that these things should all be equal. Well, how good does your data fit that model? It's called a goodness of fit test. And what's really nice about these tests is that they're done essentially in the same way. This is chapter 24. Okay, two categorical variables, the chi-squared test. So, does everyone here have a, how should I do this? Okay, I'll have to do it from scratch. So make the following table. We're gonna have, it's gonna have 4 columns in the main part of the table. It's going to have 4 columns, and it's going to have 5 rows. So we're going to have a total of 20 cells. And the 4 columns are labeled as 19, 20, 21, and 22, because we're talking about, I'll explain, the details, after we do it. But 19, 20, 21, and 22 has these 4 columns. 19, 20, 21, and 22 has these 4 columns. And the rows are going to be as follows. The first row is going to be parents' home. Okay, the first row is going to be parents' home. The second row is going to be another home. The third row is going to be your own home. So we have right now, we have parents' home, we have another person's home, we have your own home. The fourth one is going to be group quarters, kind of like a dorm or something. I'll hold it up in a second. Own home and group home. And the last one is just going to be other. Okay, so we have the following table. And let me know when you guys are all done with this, because my hand's hurting holding it up. And this is the problem where we're curious about where people live. Where do young people live? Do they live, well, it's kind of self-explanatory, at what age are people living where?
Professor, can you repeat what we use the chi test for? I know one.
Oh, we haven't gone there yet. We haven't gone. The reason of the cases, independence, and what's called goodness of fit. Okay, independence and goodness of fit. and we will, do examples of both of them because they're the same technique for both independence and goodness of fit, which is really nice. And so the technique is exactly the same, but they apply to two different situations. And actually our calculators do them in different ways. So we'll do both examples and we'll do them in different ways. Okay, so the question is, where do people live at different ages? And we took data. And we got the following. In the first cell, I want you to put 324. Okay, so of the people that we surveyed, and I'm going to go quickly through them, listing the numbers. So just so you can see where I am here. The first one is 324 people at 19 were living with their parents. To the right of that, we have 378. To the right of that, we have 337. To the right of that, we have 318. So far we have the following. You all with me so far? Yes, no, maybe so? Is anyone lagging behind?
Yes.
Okay.
Yeah, we're with you.
Okay. Next row is 37, 47, 40, and 38. So again, next row is 37, 47, 40, and 38. Next row is 116, 279, 372, 487. So that's the next one. And group home is 58, 60, 49, and 25. And you definitely want to have your calculators for this section, I'll tell you that much. Because we'll be doing a lot of calculations. So I just want to make sure, is everyone with me so far? Everyone with me?
Yes.
Hope so. And stop me if you're not. 5, 2, 3, and 9. 5, 2, 3, and 9. So this is where we're at right now. And the question is the following. Are these two categorical variables independent of each other? In other words, does age and living quarters, are they independent or are they not independent? Does one affect the other or not? Okay. And essentially what we're going to have here is a hypothesis test. The null hypothesis is that the two categorical variables are independent. The null hypothesis is the two categorical variables are independent, so independent categorical variables. That's the null hypothesis, independent categorical variables. You with me? And what do you think the alternative hypothesis is? If the null hypothesis is that the two categorical variables are independent, then what is the alternative hypothesis going to be? What is the opposite of
Dependent.
Dependence, right? The alternative hypothesis is that they're going to be dependent. Make sense?
Yes.
Okay. So how do we test it? So the beautiful thing is there's only one way of testing this, and that's to compute the chi-square value. And then just like in all the other cases, when we computed the p-value, we compared it to a certain number. In this case, what we're going to do is we're going to calculate the chi-square value and compare it to a given number. The question is, what is that number? So to that end, what I need you to do now, and this is where your calculator comes in, is we have to compute the totals for each row and each column. So we need to extend each row and column, and we have to compute the totals for each row. Do you recall what we call those totals? Because they're in the margins, right? These are the marginal totals. Okay, so let's do it. Someone, hopefully everyone, this is on page 528 in the book. So hopefully everyone has it in front of them, and I have the numbers right here, so I'll know if you're right or not. So the question is, first, what is the total for the first row? Anyone give me the total for the first row?
540.
That's the first column.
Oh, sorry.
It's okay, we're gonna need that one anyways, so it's fine to do it now. That's the first column. So the first column totals 540. And I don't mind doing columns first, it makes no difference, we'll need them both anyways. So what is, give me something else, either the next column, give me the first row, I don't care, give me something.
The first row is 1,357.
The first row is 1,357, correct. What is the next one? Or any other row or column? We're gonna need them all anyways, so let's get them done.
Next column is 766.
Next column is 766. Okay. And any other row or column? Hopefully multiple people are doing this. We can get faster if everyone picks a different row or column.
Next column is 801.
Next column is 801. Okay, excellent. And the next column or any of the other rows that we don't have yet?
The second row is 162.
Second row is 162. You said you had another one?
Last column is 877.
Last column is 877. Excellent. Next one. Next one.
1,254. Oh, the third row, sorry. 1,254.
1,254. Okay. And the next one?
192.
192 is correct. And the next one? And the next one?
19.
19. Okay. So now what is the total number? If you're late, just tell me at the end. Okay, I can't stop right in the middle. What is the total number now? Right, the total, if I add up all the cells together, what's the total number? Total number?
2,984.
2,984 is correct. 2,984. So this is the complete table. We all agree with this? Hopefully you are all doing it. If not, I guess you're not really in a position to confirm or deny it, but I checked the book and all these numbers are correct. So here's what we have to do now. This is the technique for this particular process. We have to make a new table. Okay, this new table that we create is going to look exactly the same. It's going to have the same rows and the same columns as the first, but the numbers are going to be all different. So let's go ahead and first make this new table. Let's label the rows again by parent's home, another person's home, your own place, group quarters, or other. So it's parent's home, another home, own home, and then we have group home, and then we have other, just like before. And what are the columns going to be labeled as? Just like before.
19, 20, 21, 22.
19, 20, 21, and 22, right? So here's what we're going to do differently. Take out your calculator because we're going to do a lot of work right now. And I'll do it right here on my calculator as you do it on your calculator. For each of the cells, I want you to take the number at the end of the row and the number at the bottom of the column, multiply them, and then divide by the overall total 2894. So for example, can someone, hopefully if you understood what I just said, tell me what we're going to calculate for the first one? The top left cell, which is a 19-year-old.
You're gonna
Say again,
multiply.
what is it?
You're gonna multiply 540 by 1,357 and then divide it by 2,984.
Perfect. We
What?
multiply the number at the bottom of the column by the number at the end of the row, the two totals. We multiply the two totals and then divide by the overall number 2984.
Wait, are we making another table?
Yes, we're making another, that's what I said, making another table.
Wait, hold up.
I said, making a complete new table now. A complete new table.
Can you repeat that one more time? You multiply 540 times.
You multiply 540, which is the number at the bottom of the row, by the bottom of the column, by 1357, which is the number at the end of the row, and divide by the total, which in our case is 2,984.
Okay, thank you.
When we do that, what do we get? When we do that, what do we get? Is anyone doing it? I have my number on my calculator. What do you guys get? Anyone? Is nobody doing it?
Hold on.
245.569.
Okay, so let's round to one decimal, 245.6. Even though on my calculator, I'm gonna keep all the numbers on my calculator, every single one of them,
Okay.
because I'm gonna use these numbers later in the problem. But for now, I'm gonna just, on my table, use one decimal because I don't have a lot of room. Now, what we have to do now is do the same thing for each one. So we gotta do these quickly. Okay, so
What does that number go into in the table? Under 19?
it goes into the square, which we were just working on, which was the first column, first row square.
Got it. Thank you.
Okay, you all with me?
Yes.
So now if I want to get to the one right next to it, the second column, first row, which numbers do you think I'm going to work with this time?
766 times 1357.
Good, because it's still the first row, but now it's the second column. And then what do I do with that number?
You multiply them and then divide by 2984.
And when I do that, what do I get?
348.335.
348.3. All right, we're going to round to one decimal, 348.3. And now we do the next one. As I was saying, the section's very mathy in terms of math that needs to be done, but it's not complicated mathy. It's just essentially the same one over and over and over again.
Sorry, what number did we use for this box, the one we just did?
Bottom of the row, end of the column. Every cell, use the number at the bottom of that row, sorry, the end of that row and the bottom of that column.
We used
Huh?
we used 540 times 766.
No, 540 and 7666 are two different columns.
Oh, okay.
They're in two completely different columns, right?
Your Majesty.
Whatever cell that we're currently working.
One another personally to ask ourselves some of the.
What is that?
Sorry, it was me.
Whatever cell we're currently in, you go to the bottom of that column and you go to the end of that row and you multiply those numbers and divide by the total, 2984 in our case. Every cell is going to have a different row and column that it's in. Does that make sense, what I'm saying?
Yes.
And you should get this repetition in because these problems, there's a lot of math, but we're going to, it's okay. So what do I get to? What's the next one? What's the third one going to be?
364.3.
364.3. Okay. How about the one after that?
$398.8.
Good. 398.8. And now we got to go to the second row. So now we're no longer using 1357. And what are we going to replace 1357 with?
162.
162, but we're going to do exactly the same thing. We're going to calculate the number at the bottom of the column, the number at the end of the row, multiply them, and divide by the overall total. So let's do that now for the next one.
Should be
What do we-
29.3.
How much is it going to be?
29.3.
29.3. So you did 540 times
162.
162 divided by 2984.
Yes.
And that gave us 29.3. Okay, good. Excellent. And then the next one.
41.6.
41.6. And then the next one.
43.5.
Well, you're going ahead. That's awesome. 801 times 162 divided by 2984. Yep, 43.5. So let's just go ahead. Let's fill it in. 877 times 162 divided by 2984. Hopefully we'll all get the same thing. What do you get?
47.6.
47.6. Now we go to the next row, which is going to use what number instead of 162?
1254.
1254, but we're going to do exactly the same thing, which is 540 times 1254 divided by 2984. What do I get?
226.9.
226.9. Excellent. And now the next one, which is what do you guys get?
321.9.
321.9. And then we do the next one, which is third column. What do we get?
336.6.
336.6. And then we do the next one. What do we get?
368.6.
368.6. Excelente. And then we do the next row. Last row, best row. Oh, wait, there's two more rows. Never mind. Not quite there yet. What do we get for the next one?
34.7.
34.7. And then we use 766 times 192 divided by 2984. And that gives us 49.3. And then we do, 801 times 192 divided by, okay. So let's finish it up. Let's go ahead and finish it up. You guys hopefully are all participating and you're all doing it so you can all get to the end yourself. Let's go ahead and do it. By the way, just so you know, your calculator can do all of this, but it's important to understand what your calculator is doing behind the scenes, which is why I'm actually doing it all. So these are all my numbers. Hopefully you agree.
Yes.
Okay. So did we all copy that? Are we all on the same page in terms of that? Yes, no, maybe so. This is like the whole lesson. Is this like one problem? This one problem essentially encompasses the entire lesson today. So we're doing this entire thing. We're going to walk through it step by step and go through the whole thing. So essentially what we have here is as follows. The first table we can call the observed table. The first table at the top is the observed table. Those are the ones that we actually got. Those are our actual numbers. The second table is called the expected table. These are the numbers that we expect to get if the two categorical variables are really, truly independent. Now, I didn't explain why that's the reason. I'm just giving you the algorithm. I'm just giving you the steps to solve this problem. Okay, but the second table that we created are the numbers that we would expect if the two variables really were independent. Now, when you look at all of the cells, and by the way, how many cells are there? There's 20 cells. Do the numbers in the top match the numbers in the bottom? I mean, they're not going to match perfectly, of course, but are they close? Are they in the ballpark?
Kind of.
Huh? Are they in the ballpark? Each cell on top with its counterpart on the bottom. The top is what we got. The bottom is what we should get. If they're really independent, are those numbers close? Some of them certainly are. If you look at the bottom left, for example, 5 to 3.4, those are fairly close to each other. Of course, the top left, 324 to 245, those are pretty far apart from each other. So some are close, some are not close, right? How do we know whether or not the numbers that we got are close enough? And the answer is we compute the chi-squared value. Chi is a Greek letter, kind of looks like an X, so I kind of just, make a fancy looking X. Okay, that's my chi. Okay, we're going to compute the chi-squared value. And the formula for the chi-squared value is as follows. We are going to add up, we are going to sum together. In a numerator, it's observed table is the actual outcome. Well, I don't know what you mean by in the sample size, but it's, of the 2,984 observations, these are the actual observations. 324 were here, 378 were here, 337 were here, 318 were here, and so on. This is the actual observations versus what we expect to get if we have independence. So what we're going to do is as follows. And this is not a short calculation, although luckily the calculator can do it for us. The chi-squared value is defined as follows. We are going to add up, we are going to sum observed minus expected squared over expected. So we are going to take every observed cell, subtract its counterpart, the expected cell, square that, divided by the expected, and add them all together. This is how we compute the chi-squared value. Observed minus expected squared all over expected. So for example, the first number we're going to do is we're going to take the top left observed value, which is how much?
324.
324. We are then going to subtract its counterpart's expected value, which is how much?
245.6.
245.6. Although on my calculator, I keep all the decimals. We're then going to do what to that number that we just calculated?
Square it,
Square it. And we're then going to do what?
divided by 245.6.
Exactly. And that's going to give us 25.0 approximately. So the first term is going to be 25.0. And then what we're going to do is we're going to do this for each cell and add them together. Now that's going to take a long time. So without actually doing it, I believe the book does it for us, and they do. And they get an answer of 193. I'm just going to write ... You
want potatoes or pasta?
Whatever.
Okay.
That's going to get us 193.58. Well, you don't have to make a table. You just add them all together. So, in a row, 2.50 or sorry, 25.0 something plus this, plus that, plus this, plus that, until the final at the end, you have the entire sum of how many numbers are we adding together, by the way?
20?
20, right? 5 rows. This is all on pages. Well, where we're at now, by the way, which is this calculation is on page 534. This is on page 534, where we're still adding it together, page 534. Okay, and when you add up all these numbers and you do it as accurately as possible, you get 193.58. Now, if the observed numbers and the expected numbers were really close to each other, then what would observed minus expected be approximately? What would the observed minus expected be if our observed, like 0, right? It would be close to 0, right? And when you add up lots of numbers that are close to 0, you get a very small number, right? So small numbers for chi-square correspond to the null hypothesis being correct, or at least not rejecting the null hypothesis. And big numbers for the chi-square are the opposite. Big numbers for the chi-square correspond to the null hypothesis is probably not correct, and therefore I'm going to reject it. So how do we determine this? Well, we have to look up at a chi-square table. Now, I'll share my screen here for a second. And let me load up here a chi-square table. Okay, we've had Z tables, we've had T tables, and now we have a chi-square table. So let's see if this one's good. Okay, whoops, this one right here. Okay, so here is my chi-square. Okay, let's see if this is good enough. So here is my well, here's a little chi-square table, but that's not what I want. I want something a little more expansive. Okay, so here's a chi-square table. Okay, so essentially what's going to happen is it's going to look like this. We have to determine, like we do for T, how many degrees of freedom we have in the problem. So the number of degrees of freedom, df, is equal to the following. And we'll see if anyone can figure out what these symbols mean. The number of degrees of freedom is equal to r minus 1 times c minus 1. Can anyone take a gander, without looking in the book, of what r minus 1 times c minus 1 is referring to? What is r and what is c? Let's take a guess. What is r and what is c? What is r and what is c? Anyone take a guess? R is the number of rows and c is the number of columns. So in my data, how many rows do I have?
5.
5 rows.
5 rows. So R is 5. And how many columns do I have?
4.
4 columns. So 5 minus 1 is 4. 4 minus 1 is 3. 4 times 3, we have 12 degrees of freedom. Right? So the number of degrees of freedom is 12. Now, we're going to go to the row for 12, and we're going to look for my chi-squared value. My chi-squared value was 193.58. It is way off the charts. So what can you tell me about its p-value?
Probably really big.
Big.
Oh, just kidding.
Big. Here's 12. We're off the charts. We're going off the chart this way, right? Right? Is anyone following? Hello?
Wait, can you repeat that again? Like,
12 degrees of freedom, and our chi-squared value was 193.58. Where's 193.58?
Not there.
It's way off the charts. The chart only goes up to 30, 33. And this is 193.58. It's way off the chart. Yes? Which means if we look up here at the p-values, its p-value is what? Not exactly what, because we can't calculate it, but it's approximately what?
very close to zero.
It's extremely small, right? I mean, listen, at 32.9, we're already at a p-value of 0.001, let alone 193.58. So the p-value is approximately 0. So what is the conclusion we make when we have a p-value that's approximately 0? Do we reject the null hypothesis or do we not reject the null hypothesis? What do we do in this case? Do we reject it or do we not reject it? When the p-value is extremely small, what do we do?
We don't.
Excuse me?
We don't reject it.
No. When the p-value is small, we certainly reject it. I mean, that's unfortunately, that's like everything we've been doing for the last 5 weeks.
No, I got confused because before you said small chi equals correct. The null hypothesis was correct.
Yeah, a small chi-squared value means we're on the left of the chart with a big p-value. A big chi-squared value, we're on the right of the chart with a small p-value.
Oh, okay. Yeah, that's where I got.
All p-values make us reject the null hypothesis, correct?
Yeah, okay.
Yeah, we're all with me here?
Yeah, that's much better. Thank you.
Okay, so what is our conclusion about this problem? Is living arrangements and age independent variables or not independent variables? Does it like make no difference what your age is? People are going to live in the same places no matter what? Or do we expect them to depend upon age? Which is it? Based upon this experiment that we just did.
Oh, since we're rejecting the null hypothesis, then the categorical variables are dependent of each other.
Well, we can't conclude definitively that they are, but we are certainly, the evidence is certainly pointing in that direction. Right? The evidence is certainly pointing in the direction of dependence. So therefore we reject the null hypothesis. So this is what we do for any situation where you are testing for independence of two categorical variables. It actually popped up in my life recently, not recently, but like within the last year, somebody had a question of my brother-in-law works for a either TV or radio station or something. And they were doing some kind of promotion where this and that, and he had to actually figure out some connection between two things. And he asked me, hey, how do I do this? And it actually ended up being that we had to use a chi-square test. And then one of my students last year ended up doing a project because she works. You guys know what the IB is, the International Baccalaureate? It's mostly for European schools, but I teach at an IB school. And so she had to write a math paper, and she actually ended up doing a statistical report, which ended up using the chi-square. It's just, these things, I would say, to be honest, the chi-square is probably more prevalent in standard statistical testing than T or Z. Granada Hills, yeah, there is an IB school in the Valley, Granada Hills or Chatsworth, something like that, right? This one that I teach at is actually in Burbank, but they're around. There's thousands of them in the world. The IB is a big thing. Okay, so this takes, huh?
I have a question. Is this the same like chi-square thing like in biology? Like, I don't know if
I don't know 100% about that, but what I can tell you is that last year I had a colleague who was a biology teacher, and she called me into her students to give a lecture on the chi-squared test because, you know, it's mathy and she's not really a math person. So presumably it is. That would be my guess. How does the good? Oh no, we haven't done goodness of fit test. This example is for independence. Okay, this example is for independence. Now let's do a second example, and the second example is going to be for what's called goodness of fit tests. Okay, and for those looking, the second example is on page 546. Wait, can I see the paper? Yeah, I don't have much on the paper, but I didn't write anything. I just said it. So you calculate the degrees of freedom. So you can calculate the p-value, and once you have the p-value, you make your conclusion, whether it's you reject the null hypothesis or you don't reject the null hypothesis. Yes, no, maybe so. Hello? Anyone? Okay. So the next example is on page 546. This is a different example, but it also uses chi-square. This is what's called a goodness of fit test. A goodness of fit test is where we determine how good something fits the data. So on page 546, it reads as follows. Births are not evenly distributed across the days of the week. Fewer babies are born on Saturday and Sunday than on any other day. Does that seem reasonable, that fewer babies are born on Saturday or Sunday than any other day of the week? Shouldn't, you know, people just give birth at, I mean, listen, I don't obviously give birth, but it just seems that people just give birth when they give birth. Why? The baby doesn't know that it's Saturday or Sunday. So why would there be a prevalence for people to be more likely to give birth on Monday through Friday than on Saturdays or Sundays? Anyone have an idea for this? Can anyone venture a guess as to why you think people are more likely to give birth Saturdays and Sundays than they are on, on Monday through Friday? They hold it in. I'm not a person who knows much about biology, but I don't really think that's possible. I know that my mom, when she had me, was watching a movie and her water broke, and she told me this later, that she wanted to see how the movie ended, so they waited until the movie was over before they went to the hospital. I was not her first child. I'm sure if I was her first child, she probably would have felt a greater sense of urgency. But maybe that's why I'm as screwed up as I am today. Who knows? So can anyone venture? What movie was it? That I don't know. She probably knows. She remembers things. She remembers everything. She knows the exact minute all her kids were born, and she remembers everything about everything. But unfortunately, I do not. So the reason why apparently, what does it say here? Hospitals schedule births. Yeah, so it's not, when people give birth, they give birth, but there's lots of births that are not natural, that are induced, or cesarean sections that are scheduled. And those things are going to be scheduled on days when it's cheaper for the hospital, and that's usually during the week. So taking those into account, there actually is an imbalance. Anyways, what we have here is a sample of 140 births. And here's the data. So what we're going to have is we're going to create 2 rows. The 2 rows are going to be for days, the day of the week, and birth. And Sunday shouldn't have been on the top. Sunday should be in the row itself. So here's the beginning, right? The days are Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday.
Can you stop sharing your screen, please? So we can
Oh, I'm sorry. Thank you. Thank you. I apologize. So we have here is the days of the week is the first row, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So let's fill that all in. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Okay, so those are the things. Okay. And now we have the values. So the numbers are as follows. The numbers are 13, 23, 24, 20, 27, 18, and 15. I will hold them up so you can see it. You guys all have them?
Oh, yes.
Yes, all good?
Good.
Okay. The question is as follows. We believe, or the null hypothesis, what we're trying to test is whether or not all of the proportions for the percent born on Sunday, the percent born on Monday, the percent born on Tuesday and Wednesday and Thursday and Friday and Saturday, whether they are all equal. We'll say P1 equals P2 equals P3 equals P4 equals P5 equals P6 and equals P7. The null hypothesis is that the percent of births for each day of the week is the same. This is what we're testing. Are they all the same? Is P1 equal to P2 equal P3 equal P4 equal P5 equal P6 equal P7? The alternative is going to be what? Thank you.
You got water?
Yeah. What is the, thank you. What is the alternative hypothesis going to be? It's just mashed potatoes. It's just nothing. It's just this concoction that they make. Yeah, but it's actually not bad. I've just had it for like 20, 30 days now in a row now, so not a lot of variety in this thing. So Mariah, it's a good guess. Mariah said all the equals become not equals, but actually that's not the case. Because maybe 5 of them are equal and these 2 are equal, they just are not equal to each other. There's lots of possibilities other than all 7 of them are equal. The best way to say it is the null hypothesis is that they are not all equal. This is really the best way to say it. They are not all equal. And the question is, how do we calculate this? Well, what we're going to do is we're going to make a new row in the table. And the new row in the table is going to be our expected row. So this first row, the births, is our observed. And what we're now going to do is we're going to create a new row for my expecteds. So we have the observed, all the observed values. And now it's all the expected values. So if it really was uniform and all of the proportions were equal, of the 140 total births, how many would we expect to have each day? How many would we expect to have each day if they really, really were all equal?
20.
20. So every row of this new, every entry of this new row, we're going to put in a 20.
Wait, why 20?
Well, because 1/7 of 140 is 20. If they're all equal, we expect the same amount per day.
Oh,
So 140 split up evenly into 7 days is 20 per day. Agreed?
yes.
Okay, so if they really are all equal, and we're checking to see whether or not the data fits that well, or fits that good, if they really are all equal, then they should all be 20. And now what we're going to do is we're going to compute the chi-squared value, which is going to have exactly the same formula as before. It's going to be the summation of the observed minus expected squared over the expected. And this one is actually not nearly as cumbersome as the last one. We can actually do this. So let's actually go ahead and do it on our calculators. What is the first observed minus expected? And I don't care about the negatives because we're going to score it anyway. So what is my first entry going to be? For my observed minus expected squared all over expected.
13 minus 20 squared divided by 20.
And what do I get?
2.45.
Sorry?
2.45.
2.45. And then we do the next one. Yes, no, maybe so. What are we getting for the next one?
0.45.
0.45. Good. How about the next one after that?
.8.
0.8. And the next one is the easiest one.
0.
0. I got exactly what I expected. And the next one.
2.45.
Excellent. And the next one.
0.2.
Good. And finally, the last one.
1.25.
1.25. And then we're going to add them all together. And the book does that for us. And what do we get? What do we get? Sorry?
1.6.
7.6. So my chi-squared value here is 7.6. Now the question is that chi-squared value big enough that I'm going to reject the null hypothesis? Or is it not big enough and I don't reject the null hypothesis? Well, in order to answer that, we have to again look at a chi-squared table. But before we do that, we have to know how many degrees of freedom there are. Now, we don't have rows and columns here like we did for the last example. That was a different test. That was a test for independence of two categorical variables. Here, it's a goodness of fit test. We're saying, how good does the data fit a certain model? So in this case, the degrees of freedom is just going to be the usual n minus 1. So how many pieces of data do we have here?
140.
No, well, okay, let me rephrase that. We have 140 pieces of data, but how many cells do we have? How many entries are there in my table? That's a better way of saying it.
12, right?
No, there were 7. 7 days of the week, 7 entries. Right? I might have added 7 just so I can compare my observed and my expected, but my actual original table, I just had 7. Right? Sunday through Saturday, right? Sunday, Monday, right? 13, 23, 24, 20, 27, 18, 15, 7 of them? Yes? Okay. So the degrees of freedom is going to be 6. We have 6 degrees of freedom here. So then I go to my chi-squared, and I go to 6 degrees of freedom, and I look for my 7.6. And I see that 7.6 is between these two values. So that the p-value is greater than 0.2. I don't know exactly what it is, at least not from this table. The table is too inaccurate for me to know the exact value, but I do know it's between these two numbers. So I know for a fact that the p-value is greater than 0.2. Because the p-value is greater than 0.2, what do?
You don't reject it.
You do not reject the null hypothesis. There is not enough evidence that births are not evenly distributed because the p-value is too big. Does that make sense? Are there any questions on the two approaches for tests for independence or for goodness of fit tests? Because that's chapter 24.
What was the conclusion in context again?
The conclusion is we do not reject the null hypothesis. There is not enough evidence to conclude that births are not evenly distributed. So that the null hypothesis, where they are evenly distributed, could very well still be true. We can't reject it. Even though we didn't get 20 on any day, well, we got 20 once. But even though the numbers were not all exactly 20, they weren't far enough away from 20 for us to reject the null hypothesis. Does that make sense? By the way, I saw an interesting little blurb here. This book likes to throw in little stories and things. So I was reading, I saw one today. It says, a study of deaths in bar fights showed that in 90% of the cases, the person who died started the fight. The formula? The formula is right here. You add up observed minus expected squared over expected. So a study, huh?
May I see the numbers really quickly for 1 second? Thank you.
No problem.
Okay, thank you.
Okay. And so the study of deaths in bar fights showed that in 90% of the cases, the person who died started the fight. What do you conclude from that? So Kiana says, don't start a fight because you're more likely to be the one who died. Does that seem like a reasonable conclusion based upon the data? So the answer is no, that's nonsense. Because if you think about it, if you got into a bar fight and the other person died and the police come to investigate, what do you tell them? Oh yeah, I started it. No, you don't. What do you say? You say he did it, right? You say the other guy did it. I didn't start it. I was just defending myself. He attacked me. Who's going to argue when the guy's dead? So it's on page 530, a little thing on the side. So after all, it says dead men tell no tales, and hope the bars have camera. Well, that depends. Depends what really happened. Whether you hope they had cameras or not. Anyways, so that's it. We just finished statistics, or at least this first semester of statistics. Okay. We will have it's not over yet. We have a couple weeks to go. We have 3 more classes pizza party. We should have a pizza party every day, but not when I'm on a diet. Wait till I'm off my diet, which at the rate I'm going should be like, tomorrow or something. I'm down 31.2 pounds in 30 days. So I'm doing pretty good so far.
Whoa, that's awesome.
You can kind of see my muscle definition coming out. It's a little there now. It used to be just like a lot of flab, and now you can actually see it. So I'm kind of happy about that. Orange creamsicle party. That's what I'm talking about. Orange creamsicle party. Well, thank you, Sydney. I really appreciate that. It's very sweet. How about extra? Why would I give you extra credit for me? Why? What are you saying? That doesn't even make sense. Why would I give you extra credit? For everybody, extra. I feel like Oprah now. Extra credit for everybody. You get extra credit, and you get extra credit, and you get extra credit. Will I be off my diet for Thanksgiving? Well, I decided that I will be eating a tremendous amount on Thanksgiving. Oh no, that'll just make me jealous, Cannon. You'll just lose for that. I will be eating a tremendous amount on Thanksgiving, but what I will not be doing is drinking any soda. That's gonna be my thing. I'm not gonna be drinking any soda, but I am. Chances are I'll be eating a lot because I haven't eaten a lot in. I had a cheat meal last week. I went to an all-you-can-eat a Korean barbecue, and I put on 6 pounds. And then within 2 days, it was gone. Within 2 days, it was gone. 2 days later, I'm back and I'm dropping again. So, it's like a little hurdle, a little blip in the road. So this will be the same thing. I'll eat a lot. I'll put on 6 pounds. And then 2 days later, I'll be back to where I was before. So, so I'm okay with that. It's just the continuous putting on 6 pounds every day thing that it's hard to work off. But if you do it now and again, where did I go? I went to a House of Galbi on Ventura Boulevard, just west of Sepulveda. She's saying no. Is it because you don't like it? That place rips you off, bro. I don't know. I didn't pay. I just, someone else paid. I just ate. He took me for my birthday. What do you want to say? He's the one who paid. So, well, he kind of likes it. I go to a place near my house on Sherman Way a lot. It's called Aki All You Can Eat. AC Gogi on Van Nuys. AC Gogi on Van Nuys. That's the one. That's like a minute from my house. So I used to go there a lot because it's down the block and I can just stay there for hours. Yeah, I hate that yogurt. It's disgusting. I'm like, no yogurt, please don't make me vomit. But yeah, for me, it's not the quality of the food, it's the quantity that matters. The more food they have, the better. That's what I say. So anyways, guys, 7:42. We're gonna end here, but a couple things. One, I hope everyone has a wonderful Thanksgiving. I'm gonna stop